Good day, this is an accompanying video for the report presented. This is going to briefly describe the theory behind the space vector pulse width modulation and the logic behind an algorithm created to simulate this modulation. The space vector pulse width modulation, or SVPWM, is a widely used method in inverter circuits to generate three-phase voltage. 6 switches are used to create 8 commutation states. Of the 6 switches, only 3 are controlled, the other ones do the opposite to avoid shorts in the system. This method of modulation consists of applying space voltage vectors during some fragment of time and in a specific order following a reference vector traveling within a circle. The chosen system was a 3-phase inverter. As can be seen in this image, it's made up of 3 semi-bridges. On each one of the branches there are a couple of switches bidirectional in terms of voltage and unidirectional with the current. Each extreme is connected to the same voltage source, direct voltage source, which is the one that is decided to be an alternate voltage later on. And in the middle of each pair of switches there is a connection to the 3-phase system via inductors. Taking a look at the circuit, it can be determined that there are 8 possible combinations with regards of its operation. These are dictated by a very important condition, which is no pair of switches on the same branch can be at an equal state. What I mean by this is that if this switch is closed, for example, this bottom one must be open so that there is no short in this part of the circuit. With these conditions, there is also one that prevents a branch from having 2 switches open. This is to avoid having any of these inductors open. Continuing with Clark's transform, this mathematical manipulation is quite important. Parting from this equation system, one can easily find the instantaneous voltage vectors V alpha and V beta. And looking further at this equation system, this can also provide us with 3 voltage vectors VA, VB, and VC. This by doing some arithmetic and solving for this column vector right here. And then to see clearer each vector's magnitude and phase, we can change coordinate systems passing from rectangular to polar. As I mentioned before, there are 8 possible combinations, which are called commutation states. This table here presents each generated vector with its corresponding state. These are represented by 3 bits. Each position dictates in order the bottom switch, and following the only condition mentioned previously, whatever the bottom switch does, the upper one does the opposite. So for example, if there is a 1 here, like I said, this vector only controls the bottom ones. If there is a 1 here, it means that this switch is closed and this, the upper one, is open. The vector present in the commutation state here in this table represents the voltage between 2 nodes, assuming this node right here is A, this one is B, and the last one is C. The first position corresponds to VAB, the second position corresponds to BC, the voltage between these 2 nodes, and the last one to VCA. If we take a closer look into the circuit, each value can be easily determined by analyzing its behavior. It is always going to be a combination of whether minus VDC, VDC, or 0 volts, analyzing the circuit. And finally, to obtain the director vectors, each of the previously found values must be inputted in the 3-phase space vector equation. In this image right here, we can now see all the director vectors. There are only 6, meaning that there are 2 vectors which are not represented, or so it seems, because the other 2 are called null vectors, meaning that they have 0 volt in magnitude, and they are represented by the origin of this complex plane. Generating a 3-phase system is possible now, but since the director vectors form sort of like a hexagon shape, as you can see in this image right here, the final sine wave will contain various harmonic components, increasing its total harmonic distortion, or THD. To solve this, voltage vectors are used. These are vectors located in the middle of a couple of director vectors in this space right here called sector or a quadrant. These new vectors are seen here. Look, these are the 2 director vectors, and these 2 are the voltage or intermediate vectors. These are a linear combination of the closest 2 director vectors, or the 2 limiting each quadrant, and apart from those, null vectors are also going to be used to create them. These new vectors are equally spaced within the sector. Each have a delta time fragment. This value depends on the value of n, which is the number of voltage vectors in each sector. In this case, this is going to be equal to 2. And the total time for every sector is going to be TV. This value can be found using this equation where Fs is going to be equal to 60 Hz in the case of Colombia and the previously mentioned n. Using this time value and multiplying it by delta, it results in the voltage vector's time fragment, and the sum of all deltas must be 1. Finally, regarding the use of null vectors, as mentioned earlier, and this is used in the creation of the voltage vectors. These are quite important due to its voltage value. It helps scale the voltage vectors to create a more perfect circle for the resulting sine wave to have less THD. This can be done by doing an average sum, where the directed vectors are used along with the null vectors, which provide no change in the magnitude, resulting in a lesser voltage average, and thus creating a shorter vector. To further avoid unwanted harmonic components when choosing a null vector, since we have two choices, whether it's 0, 0, 0 or 1, 1, 1, it is important to choose one where the least amount of switches change states. For example, if we're going to have a vector 0, 1, 0, the null vector following this vector is going to be 0, 0, 0, so we only change one switch and not two.
As seen on the screen, we have a very general algorithm which is used throughout the project to implement the method of space vector pulse width modulation. In the first part, parameters have to be defined, such as the number of intermediate vectors, DC voltage, and execution rate used. Then, some values are found using the parameters like the transition time between vectors, and using this time and the execution rate, the final vector size can be found, along with the error to correct some approximations realized. The control vectors are then defined, and in these control vectors, we will store the control sequence found later on. The final part of the algorithm are the for loops, which are considered the most complex part of the algorithm. Here, we are going to create a few variables. These variables are going to be delta 0, delta 1, and delta 2. These variables are going to be multiplied by the vector size found at the beginning using the parameters. And, well, they're going to be multiplied, right? The deltas with the vector size. The resulting product will define the number of loops realized for each vector. For the director vector for loops, we will define delta 1, and this is going to be related to the director vector. And for the intermediate vector for loops, we're going to define delta 1 and delta 2, which are also going to be related to director vectors. But in this case, these are going to be adjacent and will surround a sector where the intermediate vector will be located. It's also important to note that delta 0 is always going to be related to the null vector. And in each loop, different control sequences are going to be added to the control vectors that we created right here.
Continuing with the oscilloscope testing, this simple block diagram shows the connections made. This setup consists of a computer with the Typhoon Hill software outputting the algorithm and the complete system to be processed by the Hill 402, which is a hardware in the loop system, and then again outputted to the oscilloscope to visualize the final sine wave and see its frequency. This is a simple connection. Firstly, let's observe this image right here, where two output ports can be seen. There's the analog and there's the digital output, and in this next image there's a close-up on the analog output. Here we can see three labeled pin rows. So you can see right here, the most upper one is C, which is the ground connection, and then B and A are for data. The oscilloscope comes with two probes. One was connected to the most left bound connector, which is this one right here, corresponds to A0, and the other one was connected to the pin to its left, which is A1. Later in this video, we will show the oscilloscope readings to see the final signals.
The following are the results obtained. First of all, when we simulated using the oscilloscope, and the second image shows the simulation using software, Typhoon Hill. This first slide is when we had n equals 0. That means that we had no intermediate vectors. We only created the signal using only director vectors, and this can be shown, for example, in this part of the graph, also in this one, where we can see a perfect square control sequence created, and in the last graph, where we can see that we have almost like a triangular wave. And when we simulated in the oscilloscope, we had almost a bit more a wave that was resembling more like a sine wave. As we went increasing the number of intermediate vectors, we saw that there were more commutations, and this can be seen with rapid jumps from the square control sequence. This also helps reduce the total harmonic distortion in the signal, in the resultant signal in this one, where you can see that the wave is resembling more a sine wave. The same can be shown in the oscilloscope. And when we start increasing the number of intermediate vectors a lot more, we see that this can almost resemble a sine wave, so almost a perfect sine wave, which is what we were hoping to acquire for the inverser, where we have the DC, where we have a DC AC. And the only problem with this is that when we start to increase the number of intermediate vectors, we had problems with losses due to the commutations. Besides obtaining an almost perfect sine wave, we were also able to obtain almost 60 hertz frequency for each case. And we were able to figure out the direct relationship between the execution rate and the number of intermediate vectors that we are able to define for the method. This means that when we have an even bigger execution rate, we are able to increase the number of intermediate vectors by a large amount. For example, the amounts we were able to simulate were up to 40 intermediate vectors. Although this was a very slow simulation because of the high number of calculations that were made during the simulation in Typhoon.
That's all. Thanks for watching. For more detailed information, be sure to check the report sent along with this video.